Well, here we are, guys. I don't know about you, but I need a haircut. I know that. We did make it to the end of the semester, though. I'm actually really proud of all of you guys. Not only for sticking with it with the class, but for sticking with it with the class through this. It looks like we're, as a society, finally getting out of this. I don't know that we're necessarily scientifically or medically speaking getting out of this thing, but man, oh man, what a interesting trip that you guys had an opportunity to be a part of. Not a good one either. Man, oh man. Today, what I'm going to do is walk you guys through very casually the final review. This will be, I said a couple weeks ago, I said, no more lectures. Okay, well, I lied. This is the last one. This is going to be your final review. And at this moment in time, while I'm recording this, I have not decided yet on if I'm going to have you guys do another forecast assignment. This last one was pretty robust, and I'm realizing that doing these assignments when we're not face to face and hanging out in class, I think doesn't hold as much value for you guys too, which is kind of unfortunate. Because a lot of times the fun part of doing these assignments is working together with other people in class and asking questions and really stepping outside the mental box and kind of getting yourself in a place where you're thinking critically and you're trying to apply all the stuff that you've learned up until this point, the stuff we're about to go over in the final review, and then you're able to apply it basically. But unfortunately, because we're not all in the same class together, I know sometimes it can be difficult to think critically when you're not being, your mind isn't being stimulated by other people asking other questions. So anyway, let's dive into things and let's see here. There we go. We can dive into things. Here's your final review. Like I said, this is going to be super cash, so this isn't going to be anything very formal. I'm not even going to start the slides. I'm not even going to start the show over here. I'm just going to click through like you guys can click through on this. I'll load this up on the web too, so you guys can take a peek at it. But all this is a lot of the slides from earlier in class. It just maybe help you guys out instead of having to go through each individual lecture. They're all kind of in one place. But I will say this. This isn't everything. So if there's something that I don't cover on here, don't think, oh, well, that won't be on the final then. I can't put every single slide back on here so that we can walk through it, unfortunately. I just got to do the heavy hitters. So do know that as you're reviewing for the final. Yeah, just know that. Okay. Advection, we talk about a lot. We do a lot about advection, and this is just the horizontal movement of air back and forth. This is basically wind. As it says on here, wind blowing across the body of water can actually pick up. In fact, here, hold on, let me go full screen with this. Can actually pick up. The water vapor as it travels across maybe a body of water, and then it can transport that from the body of water over land. That happens here a lot of times in the summer when we talk about getting a south wind off the Gulf of Mexico, and it deposits a lot of the humidity in our area. Conduction is something that doesn't happen a lot in the atmosphere, but this is the transfer of heat directly between molecules. You can think of it as, holding a pot over a warm fire. Convection is something that happens a lot in the atmosphere. This is the transfer of heat by the mass movement of fluid, such as water and air. This is the idea behind getting summertime thunderstorms, or even non-summertime thunderstorms. You're just basically moving air, an air parcel. Remember that imaginary size of air, volume of air. It could be this room. It could be it could be the whole house. It could be the whole county. And we're just moving it one way or the other. Generally, we're moving it up when we're talking about convection and showers and thunderstorms. as air rises, it's going to expand and cool, and it cools because it expands, and so any air that sinks is going to get compressed and will eventually warm. Radiation, heat radiation from the sun helps to warm the Earth, and then we get incoming solar radiation, outgoing infrared. We can kind of put this all together, and the idea, if we move a parcel of air, let's say up the side of a mountain, we go from being 60 over 45 to eventually 45 over 45. That's when we get ourselves a cloud. And then we're down to 25 over 25 as you get to the top of the mountain. Well, what happened to that 20 degrees of dew point, all that moisture? Well, we rained it out or snowed it out on top of the mountain. You get to the other side, you're 25 over 25 still, and then as you descend down the other side of the mountain, you start compressing that air, you warm it back up, but you don't really change the dew point much, and thus you are warmer and drier on the opposite side of the mountain. That's the Rainshadow Effect. Oh, skew-tees. Oh, skew-tees. You guys are either going to love these things or hate them after this final. You're going to say, I am glad that I will never see another skew-tee again, or you're going to say, I'm going to get on pivotal weather. I'm going to figure out what the weather's going to do simply by looking at the skew-tee. And remember, reading the skew-tee, it's on a skew, so you're reading it to the side here. It's not straight up and down. So that's -10 right there, -20. You follow it up to right there. And so if I were to say, well, what's the temperature at 500 millibars, you would come here and you would follow this on a slant all the way down, and you would say somewhere around, -40 degrees C up at 500 millibars, not -10. It is not -10 or -12 or anything like that. You got to follow it along. That's why I always say it's a skewed T. It's skewed to the side. That's not why it got its name, but that's the way I remember it, and hopefully that's the way you remember it too. You can see that this one has a fair amount of instability. It's skinny cape, but for it only being 50 degrees, you've actually got a little bit of instability in there. That's reasonably impressive. All right, so the idea here is then you go up a little bit higher, and then the reason that this is 27 degrees over 27 and it starts here and not down on the ground is because we're traveling up a mountain and we get to 27 over 27, and then we go back down the mountain on the other side, and then we're 54 over 35. So we've went from 51 over 44 up the mountain, snowed it all out, and then down the other side, and now we're 54 over 35. Not as much instability. A little bit of instability, no instability, very little instability. And all that is looking at air going over a mountain. Here's our textbook definition graphic. Here's real life. This really actually happened in real life. Okay. Then, of course, we've got the wonderful arrow graphic, which you'll probably see on the final, where high pressure always goes to low pressure. All the rules apply except for when they don't. High pressure goes to low pressure, then low pressure goes to high pressure. Well, wait a second. You just said all the time high pressure always goes to low pressure. It does, except for when it doesn't. So what we have here is we've got high pressure, and then the air sinks on the outside. This is, remember, we're talking about making a tropical system here. And the reason that there's low pressure here is because we're evacuating all the air. We're lifting the air very quickly here. And so you end up with higher pressure aloft because there's more air being lifted up. All right. Coriolis Force. The 3, okay, maybe 4. Main points. So Coriolis is very important. So it causes the wind to deflect to the right of its intended path in the northern hemisphere and to the left in the southern hemisphere. But the main deal here, the thing that we care most about, is as wind speed increases, the Coriolis force increases. So a stronger wind gives you a greater deflection. And the Coriolis force increases for all wind speeds at a value of 0 at the equator to a maximum number at the poles, which is why you can't get a hurricane on the equator. You can get one close, but you can't get one on the equator. And it acts as at a right angle to the wind. It only influences direction and not speed. Now, it will react to the speed, but it won't change the speed, but it will react to it. And then we go back to this thing, which another graphic that I'm sure some of you guys will be very satisfied if you never see again. So this is the pressure gradient force versus the centrifugal force versus the Coriolis force. Remember, as you're going through the base of a trough versus the top of a ridge, because you've got the Coriolis and the centrifugal force working together, the pressure gradient force has to be a little bit larger to overcome that. And because the Coriolis force has the centrifugal force working with it, it means that there is a weaker Coriolis, which means that there is a weaker wind. Now, the Coriolis isn't causing the wind to be weaker. What we are doing is we're backing out of we're backing out of that to get to and make an estimation about the wind. Now, when the pressure gradient force and centrifugal force are working together, the Coriolis force has to be a little bit stronger to balance out that balance of the forces. Speaking of, May 4th, yesterday. So the wind is stronger because the Coriolis is stronger. And you can do some easy math in here, and you can say, okay, pressure gradient force is 2, centrifugal force 1, total force 3. So the Coriolis has to be 3. And the pressure gradient force is 2, centrifugal force is 1, total force is 1, so Coriolis force 1. So you can make some easy math out of this. All right. This is the big one. I need you guys to know, and this will likely be on the final. I mean, if I were forecasting if this were going to be on the final, this would be almost a 95 to 100% chance that you see this on the final. All right. Structure of the atmosphere, of course, as we go up, the air pressure goes down. And the higher you get, the less air there is. The temperature of the atmosphere does kind of fluctuate. We cool things down as we move up in the troposphere, but then we warm things back up to the stratosphere. So it doesn't cool down as you go up, 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 up. Eventually, it actually warms back up a little bit. And in the troposphere, that's where we get all of our weather. And what is weather, you ask? Well, if you've made it this far into the semester and you don't know what weather is yet, congratulations on making this far without knowing this. But weather is a mixture of air temperature, air pressure, humidity, cloud cover, precipitation, visibility, and wind. And you guys have probably indirectly realized this, but when I ask you guys for what's the weather, when a forecast assignment, what's the weather? Well, generally I'm asking for air temperature and dew point, humidity, the cloud cover, the chance of precipitation, and the wind. Now, visibility and air pressure, to me, are less important. But if I were an air traffic controller, it would be very important, or if I was the National Weather Service working at an airport, it would be very important. For us, and what we were trying to accomplish this semester, I didn't ask you guys that as much. However, I did ask you guys about the other stuff, which is why I'm kind of giggling and saying, if you made it through this far in the semester and you didn't know this stuff, well, hey, you made it this far. All right. Speaking of weather and weather maps, high pressure ridge, low pressure trough. You can see the trough here in the Intermountain West, the Pacific Northwest, and then the big ridge of high pressure over parts of the East Coast. This is the exact opposite of what the weather is going to look like coming up in a couple of days. Big old ridge there, trough here. You can see that your area of low pressure is up here at the aloft at 500 millibars, down here at the surface. That's probably not the most accurate representation of real life. It can happen like that, but it doesn't often happen like that. All right, let's evaporate some water. How about that? The dew point, or dew point, is the measure of how much moisture is available in the atmosphere. The textbook definition, the temperature at which the air would have to be cooled with no change in air pressure or moisture content for saturation to occur. What we care about is the higher the dew point, the more moisture there is. The lower the dew point, the less moisture there is. And it's not a relative scale, but it is a scale in which you can't say, the dew point is 50, so that is a low dew point, or that is a high dew point. I suppose if you said the dew point is 90, we could all agree that that is high, or negative 90, and we could all agree that that is low. But the dew point is one of those semi-relative terms, as it has to do with what the temperature is for if you care. If your temperature is 45 and your dew point is 44, I mean, that's a pretty high dew point relative to the temperature. And you would say, okay, well, maybe we're talking about precipitation, or at the very least, it's going to be pretty humid, And then if it were 1 degree outside and the dew point was 1 degree, you would say, okay, well, sure, that's a low dew point, but we could have freezing fog, which is a very bad thing. If any of you guys have been through freezing fog before, you know how bad that can be. And I don't know, I don't know that I've talked about freezing fog. My one story about freezing fog down here. I moved down here, and I was talking about freezing fog one day on television, and I said, "Oh yeah, we got a chance for freezing fog." And I was bombarded by a lot of people who thought that I was making something up, that it was like a made-up term. It wasn't that's not real weather. There's no such, you can't get fog below freezing, because if it were freezing, then there wouldn't be fog. You'd have just ice on the ground. And I had to explain to folks, no, that's a real thing. And I don't know that it's happened down here more than twice since I've been here. And now, the second time that I brought it up, I didn't get bombarded quite as much. And I'm hoping the third time is the charm, and people kind of get it and say, okay, freezing fog is a thing, Nick. All right, stratus clouds, cumulus clouds, cirrus clouds, nimbus clouds. I never understood why they called nimbus clouds rain clouds, because it can rain out of a cumulus cloud. I've seen it rain out of a stratus cloud. I've seen it rain out of a stratocumulus cloud, but nevertheless. High clouds, cirrus, stratus, cirrocumulus, middle clouds, alpha stratus, alpha cumulus, low clouds, stratus. Okay. Be able to match these clouds to their specific area within the atmosphere. So, you guys may remember on a previous midterm me asking, which ones are middle clouds? And then, I list all these clouds, and you have to kind of pick which ones are the mid-level clouds, or the clouds of vertical development, yada, yada, yada. You guys get it. Here's an example of D-even lift, bro. Convection, lift. Topography, lift. Convergence of air, lift. And fronts, lift. That's the different kind of ways that you can get lift. Now, once you lift that up, now we got to make some raindrops. Collision coalescence happens in clouds that are warmer than negative 15 C. These are when larger droplets hit smaller droplets. They collide and coalesce. And you could get an electrical charge out of this. And then we've got the Bergeron process, not related to the guy that hosts Dancing with the Stars. And this is with cloud tops that are colder than negative 15 C. Now this is the supercooled water droplets, and you get the accretion to either cloud nuclei or other ice that's up in the cloud. More ice means less water vapor. More water vapor, or less water vapor means more water vapor can move in. All right. Then, now that we got clouds, we got rain, then we can look for it on radar. And of course, looking on radar, if you want to do the math, you're welcome to. Or if you just want to look at radar and say, hey, it's going to rain, you can do that too. Again, green, yellow, orange, red, purple, white. I'll probably only ask one question about radar on the final. I can't imagine that I would bother you guys with more than one. We didn't really go over radar much. This was more. You guys probably remember this way back at the beginning of class. This is hopefully you grabbed enough from the radar lectures to be able to read a radar, on your favorite weather app, which is hopefully the WDAM weather app, the first alert weather app, brought to you by somebody. I don't know who our sponsor is right now. I'm not gonna lie. All right, 3 golden rules. Rule number 1, at a constant pressure, the higher the temperature of the parcel of air, the lower its density. Hot air rises. Rule number 2, air parcels not acted on by another force will move vertically, either up or down, through the atmosphere until they reach a place in the atmosphere with a similar pressure, and thus temperature, because PV equals nRT. When a parcel of air moves higher and it is still warmer than the surrounding atmosphere, it will continue to move up. Now you can flip that on its head and say if it's still colder and it's descending, it will continue to descend. All right, temperature and pressure, they are related. You pack so much air into a single point, that air is going to run into itself, and you're going to have warmer air versus, when molecules spread out, they got a lot of room, it's going to be a little cooler. Also, you're able to pack more stuff at a lower temperature because those molecules aren't moving as much. So, on the example shown here, 10 degrees C, you can pack a bunch of molecules into a single spot. I like using dice. At 45, okay, well, they're a little more energetic, so they need a little more room. And at 80 degrees C, they need a lot of room. Now, if you are to pack more stuff into a tighter place, it's going to get warmer and warmer and warmer. Because again, PV equals nRT. All right, SQTs. We showed the one a little bit earlier, but just in case you forgot, your constant temperature is the dashed red line. That's how you read it. You line up with your red line, your solid red line on the SQT, and then you got to take it back, right? You got to take it back to the side, back to the side, back to the side. Here's your dry adiabat, your constant pressure. There's the skew. Constant mixing ratio is in there as well. Saturated ascent happens at 6.5 degrees C per kilometer. Dry ascent, 9.8. The lapse rate is the difference between the two. So again, temperature, dew point, wet bulb in the middle there. Your wind profile is over on the side. And you read both the temperature and the dew point off to the side and down the little dashed constant temperature lines that are in here. So the temperature on here at 500 millibars is a little bit cooler than 10 degrees C. Not, and let me come over here. What would that be? Not 10 degrees, but negative 10 degrees. Somewhere in there. It's tough to see the dashed line on my monitor here. I'm sure you guys can see it a little bit easier on yours. If you didn't notice, I'm in a different place. Trust me, Rabbit is good. Rabbit is wise. Working from home for television now, which means I had to move the studio to a more well-lit and easier to use and no bike in the background place. And so I'm actually using old TV monitors. Let's see if I can spin that around. Yeah, you see the TV monitor right there. It's just an old 24-inch 720p Element TV. So I can't see detail very well, as you can imagine, versus before when I was running on actual computer monitors. Okay, so looking at this one's a little bit easier to pick out where the temperature lines are. So there's 0 degrees. You follow that line up to where the temperature is. and you're right there. So at 500 millibars, we can follow this over. You're somewhere, we can take this back, they're around -5 degrees C, give or take. You've got your super adiabatic foot on here. You're going your dry adiabatically until you get to saturation. Your constant mixing ratio is in here. Once you get there, you get some clouds, and then you move up. You've got a little bit of an inversion. It's very dry, and then you get up a little bit further, and the temperature and the dew point get a little bit closer together, so you've got maybe some cumulus clouds, hey, hey, and then it's very dry, and then some cirrus clouds, hey, hey. And this picture was taken at the same time that this SKU-T was grabbed, back in 2014, in August. There's an example of what it looks like on paper, what it looks like in real life. It's taken outside the TV station. All right. So now we can mix our air ups vertically. We get surface heating that drives vertical mixing in the atmosphere. You can look at it, and sometimes you can get a lot of vertical mixing, and then you get your super adiabatic layer. And again, we had that here too. Super adiabatic. Down here, we call that the foot. Not to be confused with Teenage Mutant Ninja Turtles. Your super adiabatic foot down there. Go back down. And that's going to be driving vertical mixing. That extra little boost of heating at the surface is going to be driving vertical mixing. And so you can see we had a day here. We had a day here where we were waiting for vertical mixing to get going so that we could clear out of the cloud cover. So we had clouds in the morning. This is at 7 a.m. And then we were at 10 a.m. And then by the time we got to 1 o'clock in the afternoon, we had vertical mixing going, and we were able to clear out of the cloud cover where we were socked in a little bit earlier in the morning. Frontal passage. You can see that on the SKU-T on the left. Radar on the right. Too far. You see the front, here it comes, and you can see how the wind profile and the SKU-T and the hodograph all change. All right, the roll of lift. Do you even lift, bro? By the way, just in case anyone was curious, not that you are or anything, but I've got another V8 this morning. These things are terrific. Man, so good. Okay, back to the roll of lift. Synoptic scale lift. This happens over a very long period of time. This is conditioning the environment. This can initiate storms. It can. Or it can allow for the initiation of storms. But if you only have synoptic scale lift, chances are you're only going to have elevated thunderstorms. These are probably not going to be surface-based. If you are only seeing thunderstorms or any kind of precipitation based on synoptic scale lift, not going to happen very often for you. Mesoscale lift, this is on the duration of minutes to hours. This is kind of the initiation of a lot of the thunderstorms and the potentially severe weather that we deal with. This is going to be focused along boundaries, dry lines, fronts, or terrain. So, you get out into Colorado, for example, you get a little thunderstorm going up the side of a mountain. Storm scale lift happens over the course of just minutes, and this is mainly inside of a storm, helping storms propagate within supercells, squall lines, there we go, and MCSs. Speaking of storm scale lift, the stream had already begun. You can get an idea of storm scale lift in here. There's a big hail hail core in there as well. All right. So synoptic scale lift, you're getting about 10 centimeters over 6 hours. So you're talking about 2 kilometer of ascent. Is not a lot. Again, you're making clouds at this point. You're not making storms. You get meter per second over an hour. So you're talking about 3,600 meters of ascent in an hour. So that's right along a boundary or a front. That's going to help you with initiation. But that storm scale lift where you're moving at like 10 meters a second, you're getting 9,000 meters or 27,000 feet of ascent over the course of 15 minutes is going to be what's going to propagate your thunderstorm itself, and that's going to hold up the hail, which is going to differentiate things in the cloud, which is going to give you your charge, which is going to break out some lightning, which is a thunderstorm. All right, there's your 6 hours of 10 centimeter per second. I mean, like you're not getting that much out of a synoptic scale lift. I mean, you just aren't. Mesoscale lift is going to give you a little more. I mean, that's decent. That'll get things up and moving for sure. But storm scale is definitely where you want to be if you're trying to get yourself some rain and some thunderstorm activity. It's going to be a little easier to hold up a hailstone in this versus that. I mean, you just don't have a lot of oomph with that. All right. Air masses. Now, you guys probably remember this from taking weather and climate down here at USM, maybe as freshmen or sophomores. Your continental polar, continental tropical, maritime polar, maritime tropical, where these air masses run into each other. It tends to be where most of our weather happens. And then, of course, the leading edge of these air masses are the fronts. So, here in South Mississippi, we get, continental tropical, we get continental polar, we get maritime tropical. So, we're at the convergence of a couple of different air masses on a semi-regular basis. And again, the leading edge of these air masses are called fronts. In general, we got 4 fronts that we care about: cold, warm, stationary, and occluded. And really, we only care about the cold fronts and warm fronts in this class because stationary fronts don't often give you much in the way of severe weather unless you're in the southern plains in the spring and you've got the dry line set up as well. And an occluded front, while that may help you get a little bit of snow, in maybe a little bit of wintry precip, you're probably not going to see much in the way of severe weather. All right, your mid-latitude cyclone development. Cold front, the air doesn't go straight. It kind of hits that leading edge and kind of bends back and around, and it kind of goes toward either the area of low pressure or back off to the away from the area of low pressure. I was going to say back off to the west, but I suppose if we're in the southern hemisphere, it would be going back off to the east. And then air moves across the front and ascends. So the atmosphere is trying to cool the cool side, or warm the cool side and cool the warm side. The idea is that the atmosphere just wants to balance itself out. And I know you know where this is going when I start to talk about warming a cool side and cooling a warm side and cooling the cool side and warming the warm side. Yeah, we're about to get into supercells and everything else here in a couple of minutes. But the stages of a cyclone here, you got 2 areas of high pressure along a stationary boundary, and then, you start spinning some air in there, and eventually you start roping it up, and eventually you occlude it out, and then it dies. The most likely area that you would see a dry line in here, and this may be a question you see on the final, would be a good answer for that would be either, 3 or 4. You could probably get one at 5. And I've seen them happen at 2, but 3 or 4 is going to be your best bet. Finding a front. Well, suppose all these temperatures are in Celsius. You just basically connect the dots, and there's your front, and it's going to be right in there. The cold air is up to the north, the warm air is down to the bottom. Temperatures in Celsius there. There's your key over on the side. So you go from being about 90 degrees underneath that 30C area, all the way up to about, 35 or so north. And that actually happens along the Texas Panhandle quite a bit, which is why it's so windy. Because remember, pressure and temperature are related, so you can infer that there's probably a tight pressure gradient there because there is such a drastic change in temperature, and thus you're probably going to end up with a fair amount of wind. Where do our lows come from? Well, the Gulf of Alaska, Alberta, east side of the Rockies, East Texas, Oklahoma, and Arkansas. You can get them along the Gulf Coast, and you can make them in the Carolinas. The lows that form in Arkansas, East Texas, Oklahoma, Louisiana, those are the ones that cause us the most issues. The tornadoes that came through here the last couple of weeks have been from areas of low pressure on the lee side of the Rockies, or the ones that form in East Texas. If you want snow down here, generally you want a Gulf low sometime in January or February to form, and you need to have cold air in place, and then as it goes flying by, it'll give us a chance for a little bit of snow. All right, so let's put it all together. So what do we have here? Well, we've got a new area in the Pacific Northwest coming onshore. We've got a cold high in South Dakota, big ridge of high pressure starting to dive south out of Canada. The cold front stretches from Michigan to Oklahoma. We also have a dry line from about Tulsa back to about El Paso. And we've got some modified high pressure in the Carolinas. Why, oh why, is there no severe weather along the dry line? Well, let's take a peek in here. Well, it says marginal risk for tornado as your possible HAZ type, but a lot like the assignment that we just did. Why is there no severe weather anticipated along the dry line? Well, in this particular case, where I dropped my little thumbtack here and picked out my SKU-T, you'll notice that we've got a pretty decent inversion setup. So yes, while we have a fair amount of instability aloft, a mixed layer cape of 1,500, that's moot because of the inversion that's set up. We're probably not able to get stuff surface-based, therefore the tornado threat is going to be a fair amount lower. You probably still get a little bit of hail out of this, I suppose, and you can see that the significant hail underneath the sounding analogs over there. But I'll say that the overall threat for severe weather is pretty low, which is also why there's no thunderstorms along the dry line. The inversion that's set up on top of that, just to kind of poke in here, we don't really have a lot of forcing, no omega over here happening, so we're probably not too concerned about severe weather. All right, the old trophiness, talking trophiness, the made-up term that doesn't actually exist. The troughs are broken into quadrants. We got left front, left rear, right rear. Say that 3 times fast. And how they are tilted, and we'll get to that here in a second, I believe, maybe. Yes, haha, okay, so how they're tilted matters. We'll get to that in a second. Okay, convergence versus divergence going into a trough. Of course, as air goes through the trough, remember all the way back at the beginning of this lecture, we talked about how air through a trough slows down. Well, as it slows down, you get convergence, like traffic. As people slam on the brakes in front of you, then you slam on the brakes, the people behind you slam on the brakes. You get convergence. You all run into each other. Coming out of a trough and getting past all that traffic, you can floor it again, and so you get divergence because you gun it once you get by what everyone's rubbernecking about on the side of the road. Say there's a tire or something on the side of the road and everyone's slowing down to look at it, and you floor it because you're going, we slowed down for what? You take off, well, the guy behind you hasn't taken off yet, you get divergence. There's more space between you and the car behind you, the air parcel behind you, whatever. So you get convergence going into a trough. You can see everybody's rubbernecking at the big L on the left-hand side there as air is passing through. And then the comparison between what's happening in the upper levels versus what's happening in the lower levels. Of course, you have convergence happening as you go through a trough aloft. And that convergence is happening where there's a ridge of high pressure. Then you have divergence happening out of the trough, and you're getting that where there is a surface low pressure underneath where you're pulling in warm air off of the south, or the southern hemisphere from the north. Okay. Your troughs, you've got two positively tilted troughs on here. They can be negatively tilted, and this has to do with as you look, right? Remember we went over this? As you go through the trough, it's like looking at maps for topography. You find where are your geopotential heights close to each other, and that's the base of the trough. So you're very positively tilted, not quite as positively tilted, and in this case, negatively tilted. A negatively tilted trough gets really interesting because this causes cold air advection in the upper levels of the atmosphere. And you can do this when you've got warm, humid air below it. And what you can also do is a strong jet streak can cause this to basically, it allows you to rope around the colder air aloft on top of the warmer air underneath, thus giving you way more instability. And this is also what happened with the recent bouts of severe weather in April down here, is we had, I think only one of those was truly negatively tilted, but we had a negatively tilted trough over the top of us, and we ended up with the 2 EF4s and 1 EF3 tornado on the same day in roughly the same area, which is incredible down here. The last time that happened, that we had 2 EF3 or greater tornadoes on the same day. Not at the same time, just on the same day down here was 1992. We have, on record at least, never had 2 EF4s on the ground at the same time. 2 EF3s on the ground at the same time. We have never had 2 EF4s in the same day. It was a big deal down here a couple weeks ago. Okay. And then jet streaks. Speaking of jet streaks, you get an increase in deep layer of vertical wind shear with a jet streak. The same process that can produce vertical motion also changes the wind profile. Most notable in the exit region, where you've got ageostrophic, low-level winds that cross under the jet. You guys remember that, right, from lecture? Well, if you don't, good news. We're going to talk about it right now. Your straight jet streak model, so if we're not going to curve our jet, if we're just, basically we got a flat jet and we're just going left to right. The air entering the jet streak is sinking on the cool side and rising on the warm side, so you're warming the cool side, cooling the warm side. As you exit the jet streak, it's rising on the cool side and sinking on the warm side. Or in this case, it would be cooling the cool and warming the warm. So in the left exit region, the air moves through the jet streak, then it encounters a stronger temperature gradient when entering and a weaker one when exiting. The response in the exit region is to strengthen the gradient, which requires cooling on the cool side and warming the warm side, because it wants to keep the gradient that it had, that tighter, stronger temperature gradient. This leads to an enhancement in the low-level southerly winds beneath the exit region of the jet, where you've got west winds aloft. So you basically put yourself in an area where you're increasing wind from the south, underneath where you're increasing wind from the west, and that creates a favorable shear profile for severe weather if you've got enough instability, and chances are you probably do. So looking down from above, this is what it looks like: rising air, sinking air, rising air, sinking air. You've got yellow in the upper levels, red in the lower levels. So in the entrance region, in the lower level, you've got a north wind. And this makes sense because, you could say, well, on the backside of a jet, you're probably on the backside of a cold front. On the flip side, in the exit region, as the air's coming through, you are moving south to north in the lower levels. And that would make sense, too, because you're probably hanging out near a warm front. And so here's an example of what it may look like when looking at a 300 millibar chart. You got your sinking air, your rising air, and your rising air, and your sinking air in here. And you can see the jet is right in here. That's the yellow shaded area on the wind barbs right here. And if you were an area of low pressure, you'd probably be hanging out kind of somewhere up in here. Your warm front is over here. The cold front is back over here. You've got another little area of low pressure, maybe a little troughiness happening back over here. Big ridge of high pressure down to the south. Okay, this all makes sense. Now, if you're looking at it from top down, and again, I can't get this to animate for you guys, but you're coming in that way in the upper levels, and you're coming from the south in the lower levels. And then when you're looking at, remember this is the one where it goes in circles, where you're sinking here, you're going here, you're lifting here, you're going back to the south here, when it's coming at you. And so you end up with, hold on, let me go back here. Aha. So as it's coming at you, right into your living room like that, you end up with air that's doing kind of a circle motion like this as it's coming at you. That's the one nice thing about having a camera is I can kind of highlight these things a little, maybe a little better. So as it's, so you've got the air kind of rotating if you're looking straight at it. That also means that if I'm coming into your living room and I'm pulling air in, if I'm coming into your living room, I'm pulling in air from the south, and that would be the south, right, for you guys? Yeah, south. I'm having to do this backwards. So anyway, you're pulling it in from the south underneath an area where you've got the wind flying by in from the west. Slides, there we go. Okay, so jet streak notes. So jet streaks aren't obviously always straight. Oftentimes they're either going around or through the base of a trough. As they do so, you can either amplify or de-amplify the trough as it slides through. Yeah, that's all really that I'm going to hold you guys to on that. Okay. 500 millibar maps. If you're not, based on the last two assignments, you guys have a pretty good idea about how to read all this stuff. But just really quickly, 500 millibar maps, good place to look for vorticity and basically wind. It shows the troughs pretty well. Your vorticity, again, on the maps that I give you guys, you'll be looking for the shaded areas, the red shaded areas, as a place where you've got a fair amount of positive vorticity advection. 700 millibar maps, you're looking at wind and vertical motion. This is where vertical velocity becomes pretty important to look at. 850 millibar maps, the dew point and temperature and vertical motion are important on these. Those are kind of the most important ones for us. 925, we're basically just looking at temperature and dew point here. This is going to give you guys a good idea about where fronts are going to be laid out. Terms to know, terms to know, terms to know. These are the big ones too. Make sure you put these to reasonable memory, or at least you have them at arm's length, at arm's reach. Okay, severe thunderstorms. Here we go. Let's have some fun. Inflow coming in from the south side in the warm side. The outflow comes from the north side on the cool side. The main updraft is in the center. You can get outlier updrafts. How do you make a tornado? A lot of you guys got this right on the midterm. Good job. Sorry, I need to take a sip. Did a good job. The source of the spin, the strength of the updraft, and the coolness of the downdraft have to reach certain unknowable thresholds for each individual storm. Like we just can't know these things. And so they may seem very frequent down here, but to get these things to happen at the right place at the right time, in the right amounts, is pretty difficult. Not only to forecast, but just kind of in general. I mean, you know, so people ask all the time. They say, "Well, what's the? Am I going to get a tornado?" And I have to tell them, I don't know if you're going to get a tornado. Unfortunately, I can't know that because there are certain unknowable things that come with making a tornado in a specific place at a specific time. That's the toughest part. When you're going back and looking at radar, you can find a mature supercell. It kind of has a fan look with a hook in the southwestmost portion of the storm. The hook, likely where the tornado is, if there is one. All right. So let's when you're putting together your forecast, you got to build that checklist. You guys remember this, and then you got to cross-examine your data. You can look at all the forecast models you want. There's an image of what our weather center looked like many moons ago when I first started cleaning it up. And then we hired Patrick, and Patrick has a gift for organization, and man oh man did he make it look a whole lot better. So anyway, here's a look at all the forecast models that we'll use. I don't think I did this to you guys on the midterm, but I'll probably do it to you on the final, which is pick the one weather model that isn't an actual weather model. So if you have all of these committed to a piece of paper, or if you've got, again, these things at arm's length, just be able to pick out the one that is not a weather model. You know, for example, if I listed, you know, all of these, and then in here I also put the GLP, no, hold on, the you know me, you know, I don't know. That's a reference that probably like one person gets. Anyway, yeah, you'd just be able to pick out the one that isn't. All right, using MOS data. Now, we didn't get into this much in this class. Now, usually I do, but given this course and how we had a weird time on the second half of this course, we didn't really do much of this MOS data. What I'm probably only going to hold you guys to on this is being able to pick out what the temperature is going to be at a certain time on a certain day, or the dew point at a certain time on a certain day. So go back and review your lecture notes on this one for how to read these. And I know we didn't go over it very much, so again, I'm not going to hold you guys' feet to the fire on this like I would if we were in class. But, you know, say at 21Z, the temperature is going to be 73. You know, what's the high temperature on November 30th? The high temperature on November 30th is 75. Stuff like that. And again, going back to that 0Z, make sure you know how to read Zulu time. 6 hours back when we fall back, 5 hours so when we spring forward. So we're at 5 hours right now. So there's your midterm. There's your final review. Hopefully this is helpful and helps you guys kind of put things together and gets you guys ready for the final coming up on May 12th. Again, I still haven't put the final together completely, and it may be a take-home, it may not. I haven't decided how we're going to do the last assignment, if we're going to do one either. I'm going to decide that today. Seeing as how the final is next week, I'll leave that to your guys' imagination about where I'm going to go for that. So anyway, hopefully this helped. If you have any questions, feel free to shoot me an email, and I'll be happy to help answer any questions.